Now, the next thing that we want to do is, given this idea that the Wasserstein distance minimization is going to end us up with having the data distribution, um, the question that we want to answer is that how we can incorporate this Wasserstein distance into our uh, training algorithm. And the question that might come to your mind is that it's true that we know vanilla GAN is minimizing JS, but we did not actually start with trying to minimize JS. We eventually started with this intuitive min-max game, and then we finally showed that this is equivalent to minimizing the JS. But here, we're not doing this. So how can we start from the output of the generator and somehow estimate the Wasserstein distance and then try to minimize it? So this is a big thing, right? So the idea is that, again, we're going to do it here implicitly. So of course, we're not going to do it explicitly because we cannot do it. And through this implicit definition, we're eventually going to define discriminator again. So this discriminator is going to show up again, and we're going to end up with the same architecture as we had before. Now, the other point is that, okay, if we want to minimize Wasserstein distance, we need to be able to estimate it, right? And if we want to estimate or calculate it based on the definition we have seen for the Wasserstein distance, this sounds something quite impractical. The point is that we don't really need to use that guy. We can actually use a dual form of it, which is called Kontrovich-Rubinstein duality. That duality, even though it has a very fancy name, it's not very complicated and gonna simplify everything. So we can easily estimate everything and we can minimize it. So we're gonna see these two different things, and this is going to conclude the Wasserstein GAN for us. So let's start with forming this implicit Wasserstein distance minimization. So the original GAN, the vanilla GAN that we had, we showed that that min-max game is eventually solving this problem. So it's somehow finding not the exact JS, but an estimate of the JS, right? Estimate of JS divergence between or data distribution P and the model P hat, right? And then we are minimizing over all possible P hat values. And then this is the one which is given to us as the P hat star, or the output, the distribution learned by the generator. The point is that if we could solve this problem, this is going to exactly, I mean, P hat should be exactly P. And then we could say, okay, we hope that when we do it computationally by a model, by a generator, then we're eventually going to end up having a good approximate of the data distribution. So how we do it using a generator, we eventually define a generator, right? And then we minimize it over all possible generators. Now, if we want to do the same thing implicitly with Wasserstein distance, we're going to replace this JS distance divergence here with the Wasserstein distance here. So I'm going to write it down, the Wasserstein distance between P and P hat. And I assume that right now that I'm able to compute this distance. We're going to talk about it later. And then I just think about having access to all possible distributions. And then if we find the one which is minimizing this Wasserstein distance, say P at a star, this is going to be exactly the data distribution, right? Now, I should replace the definition of this guy here, so I'm going to replace it here, right? And we do know that this is a very complicated thing to do because eventually we don't have access to this pi space, the coupling set here. But we're going to get rid of it. Now, we want to solve this problem, but we don't want to solve it by directly going over P hat nor directly going over Q. We want to do it implicitly, meaning that instead of P hat, we're going to play around with a generator. Instead of having access to Q, we need to have access to something more practical, which is computationally feasible. Eventually, it's going to be the discriminator. Now, let's take a look at this one. So first, let's get rid of this issue with Q. So it's pretty much impossible that we search over such a space of pi, and we want to somehow do this minimization, inner minimization. We want to do it in some alternative form. And this is where we're gonna need the Kontrovich-Rubinstein duality. Now, to define Kontrovich-Rubinstein duality, we need to have this a bit of preliminaries. So the first thing is Lipschitz continuity. So Lipschitz continuity is, again, having a nice name, but it's not very complicated thing. It's eventually a more, consistent or more restricted form of being differentiable and well defined. So say I have one function. This function gets any point, any data sample, and gives me one real output, right? It could be a number, it could be a vector, anything. I don't care. Now, I'm going to say that this guy, f, is Lipschitz if I have 2 point x and x hat. Say they are two different samples, two different data points, possible data points. And then I compute the difference between these, the output of the function. So this is the distance between the outputs of the function. So when x and x hat is passed through that function, the output of that function going to have, there are two different values, the distance between these two values. This guy should be always less than or equal by some constant L, which we call it Lipschitz constant. And this L Lipschitz function is eventually L is exactly this value. So this is L Lipschitz, one constant, times the difference between 2 points, x and x. Now, you might say, what do you mean by this? But this is not hard for you to see that this L is somehow capturing a kind of bound on the gradient of this function f. Just think about the case where f is a scalar function. X is a scalar, f is a scalar. Now, the difference between 2 points of x and x hat, if x and x hat are very close points, the difference between these two is eventually the derivative times the difference between x and x hat. Now, what you want this difference to be smaller than some constant times the difference between x and x hat. So this means that the derivative of your function f, this point, the 2 points which are very close, x and x hat, say, so the derivative in that neighborhood should not be very, very large. So it eventually cannot exceed a constant L, right? And now you want this to happen everywhere. So it means somehow you want your derivative to be quite constant, bounded everywhere. And this is eventually the form of definition that Lipschitz is giving us. So it's somehow guaranteeing that if I give two different points to my function, the output of my function is not going to increasingly go up, right? So if x and x hat are very different, they are like hugely different, this f of x and f of x hat could be still hugely different. So it doesn't want your function to be bounded. So you give a infinite input to it, the output of the function could still be infinite. It doesn't care. The point is that when x and x hat are quite close, what we want that the output of the functions is still close. How close they are, well, we can define some constant L and we put it as a bound. But we don't really care how close they are. We don't want it to be infinite, right? So why this is important? Because for many functions, which are for us neural networks, we want the output to be not extremely sensitive to the change of the input, right? If I change the input slightly, then the output crazy goes up, right? I don't want this to happen. And because of this, we are defining this Lipschitz property. So this Lipschitz property is kind of property in most analytic works in machine learning. We usually put it on our neural networks. We won't, because we want this to be. If it's not the case, then that neural networks is eventually not very useful for us, like not very reliable. Now, if you want to think about it graphically, then for a scalar function, it's gonna look like this, right? So this line that you see here is sloped L. This other line is sloped minus L. And what I want that every single point, my derivative is somehow not exceeding this bound, right? So it's not going to be out of this range. And I don't care where I put my point. I always want these two lines to somehow limit the slope of the function, right? So the function here is very steep, but still the slope is below this line. Here it's not that asleep, it's below this line, and so on, right? So somehow if you just take these two crossing regions and you just pass it through over exactly on your function, you always want your function to be inside that region, right? And this is the kind of intuitive illustration of the Lipschitz property. Now, moral of the story, you have a Lipschitz function, you have a kind of stable function, and this is a kind of well-defined function, right? Now, we can define a set of all Lipschitz function, right? So we have a set L, which includes all L Lipschitz function. So say, for example, L equal by 1, then it's one Lipschitz function. It means that for the function where this inequality here is happening with L equal by 1, and I am collecting all of these functions instead, it's going to be this space of Lipschitz functions. Now, the point is that this space is not including all the functions, because all of us can come up with some examples like crazy exponential functions where they are not Lipschitz, right? And when they are not Lipschitz, then they are not included in this function. So this is not the set of all possible functions, it's the set of functions which have Lipschitz property, which is more limited. Now, one thing that you should pay attention, you should always think when we are working with neural networks and machine learning, we should always think about all of these definitions in computational form. And what does it mean in computational form? It means that when we think of a set of functions computationally, we simply mean we have a model, right? And this model has a bunch of weights. And those weights are, when we change them, the function is going to change, right? The parameters of the neural network. Now, when we think of a function set, we eventually think of a model, right? An architecture, a neural network. That neural network, we play with the parameters there to just realize different functions, right? Now, if I want to somehow limit that set of functions to be Lipschitz, it means that I should think of only those parameters for this model. So this is what I'm showing here with set WL. So say I want them to be a Lipschitz. So I want this neural network to be a Lipschitz. For the moment, forget about the value of L. I want it to be a Lipschitz. This means that I want the output of this neural network to somehow behave normally. So if I change the input slightly, the output also changes. Not crazy, right? And the point here is that if I want to do it computationally, I need to limit my parameters. So the parameters of that model should be somehow limited to the set. I'm showing it with set W here. The kind of set that it somehow guarantees that your function is Lipschitz, right? So computational thinking about it, this set of all Lipschitz function is eventually a set of model parameters, right? And then the question is, how can I find out the right choice of this W? Okay, this is a bit of challenging thing. And we're going to briefly talk about it. But in practice, we can come up with some tricks that do this for us. Now, the next thing is that the Kontrovich-Rubinstein duality itself. So this is now easy to define. Now, what we wanted to do, we wanted to find out the Wasserstein distance. And if you remember, this Wasserstein distance was minimum over all of those coupling distributions, right? But Kontrovich and Rubinstein, I mean, I said this nice story also in the lecture, that Kontrovich is quite well-known figure. He is the one who has worked, I mean, he's somehow known as the father of linear programming. And Rubinstein was his PhD student. And they came up with lots of works in that, functional and measure theory. And then this is why we call it Kontrovich-Rubinstein duality after them. So the idea here, it says that instead of going through that complicated definition, you can eventually find it in this form. So go ahead, you have two distribution P and P hat. Forget about their joint distribution. Just go ahead with distribution P and take one arbitrary function D. The only thing that this function D needs to have is to be one Lipschitz. If this function is one Lipschitz, then I put it here. and I compute this expectation with respect to P, the data distribution. I get the same function. This time, I take the expectation with respect to P hat, which is the model distribution, right? And now I am going to subtract the first distribution from the second one. This is going to be some lower bound on the Wasserstein distance. And now I look for every possible one Lipschitz D, so any possible one Lipschitz D, and I maximize over all of these choices. This is going to give me the Wasserstein distance. So this guy, as compared to the previous definition, is much easier for us to approximate in practice. Why? Okay, look at this D. How we can realize this D? Easily using a neural network, a computational model, right? Now, I have a computational model. I'm going to put it here, and I'm going to put it here. Now, I want to compute, average it over, or take the expectation with respect to model distribution and data distribution. I can do them by averaging, right? I can estimate these expectations using the data, the model sample and data sample, right? So I have a neural network. I compute it at a bunch of data samples. I average it. It's going to give me the first term. I have the same neural network. I compute it at a bunch of model samples. I average it. It's going to give me the second term, right? And now that I have these two, if I go over all possible parameters of my neural network and maximize this difference, I'm going to end up with an estimate of this guy, right? So I can do it now computationally. So this is the key point that I wanted to mention here. So in practice, you can easily do this. You only need to have this D function here to be a neural network, right? A computational model with a bunch of parameters phi. Now you put this d phi here. Once you compute this expectation using sampling from the model, so this is what sample data samples. This is why I put hat here. And once again, using samples from the model. Again, we have a hat here and the same neural network here, right? Now that I have this difference here, I am going to maximize it over all possible choices of phi. The only difference here is that I should focus on the set where this model is going to be a Lipschitz, right? One Lipschitz. So this is the only difference here happening, right? And as I promised you, I'm going to show you how you can do restrict this your phi to be within this set. But if you can manage to have this set somehow focused or concentrated somewhere, then you can simply do the maximization over this set, and then you can get an estimate of the Wasserstein distance. So this is a good thing because right now we can eventually estimate this Wasserstein distance, and this is what we need because we, at the end of the day, we want to computationally estimate it and then minimize it, right? So that's the final conclusion here. So if I take that idea, I wanted to just minimize this Wasserstein distance, and instead of, and we define it to be this form, right? I wanted to do this, minimize this guy, and we saw the definition, but Kontrovic-Rubinstein duality is going to give us this alternative form, and this is a kind of computationally feasible form, right? So I can eventually estimate my Wasserstein distance using one neural network D. And what does this neural network D need? This needs samples from data, so data samples, and samples the outputs of my generator, right? So X should go here, X should go here, and then I compute out of it the Wasserstein distance. So this guy is going to give me the Wasserstein distance. So if I take samples from data, I take samples from model, and I give them here, then I'm going to get different Y values. So once I just average it over data distribution, once over the model. So this samples from the model, and then this is going to be estimated the Wasserstein distance. So this guy is exactly doing what the discriminator do it in the vanilla GAN. And this is why I told you that this is again going to be GAN. This is not going to be something new. The only difference here is that my discriminator in this case is supposed to be one Lipschitz, right? Meaning that those parameter files should not take me to a region, to a kind of neural network, which is going to behave crazy different when the input is slightly changed, right? So now, if we look at this here, so we are somehow getting rid of this part. So we have one inner loop where we are doing a maximization. We can do it computationally now, as I showed you here. But the point here is that at the end of the day, I need to minimize everything with respect to p hat, the model, the generator distribution. And how can I do it? Of course, we have done it before using a generator. We are going to do it again the same way. So this means that instead of thinking about p hat, I am going to think about the output of a real generator, G, and then that generator is going to take some sample from the latent space and process it into x hat, right? And then instead of defining p star to be the output of minimization over all distributions p hat, I'm going to just replace it with a generator, right? So I'm going to find the generator whose output is going to minimize this guy, right? So now instead of x, I'm going to keep x. So this is the data distribution. For the second one, I needed to have x here and then distributed with this p hat distribution. Now I'm going to say this is the output of generator, gz, and then z is distributed with the latent distribution, right? And now if I solve this problem, I'm going to get a G star. And that G star, even though I don't know exactly its output distribution, I can say that that output distribution is going to be close to the data distribution, right? So it's a kind of implicit way of minimizing with respect to data distribution, as we did before. So this is going to again end us up with one GAN distribution. So we're going to start with latent. We're going to pass it through a generator. We get a sample from the model. So this is a very easy thing to do. I also have data samples, which is my training samples. Now I'm going to give all of these samples into my discriminator, and out of this, the output of this discriminator, I can estimate the KL the Wasserstein distance between uh, P and P hat. And given that now everything here is parameterized by discriminator and generator, I can say that this Wasserstein distance is depending on my choice of generator and choice of discriminator, right? And the whole purpose that I have is to just first maximize with respect to D, given this maximization here. And then I minimize it with respect to G, given this other minimization here, right? And this is what we call it Wasserstein GAN, right? So in a form of way, if we want to think about a Wasserstein GAN in a computational way, so it's a GAN. So we have a GAN. It has a generator with parameters W. It has a discriminator with parameter phi. But one thing that we do know here is that there is a set phi1 where every single set of model parameters, discriminator model parameters here is going to be guaranteed to be one Lipschitz, right? So I do have access to this one. And then I am going to have this loss term, which is going to be a function of my discriminator network and my generator network. I once maximize it with respect to discriminator and then minimize it with respect to generator. So, and this loss function is defined in this form, right? So it's going to be the expectation of the discriminator output computed over data samples, and then expectation of the output of discriminator again when it's computed at the outputs of the generator. Yeah. And the average to find the output of the generator, we simply need to sample a latent sample and then pass it through the generator network. So that's it. So again, as I said, we have latent, it passes through generator, we get it something here, and out of that thing we can have some risk term. Now this risk term is proportional to the Wasserstein distance, and we can compute the gradient, right? And of course, if you want to, when you compute the gradient, you are eventually, based on the gradient of this guy with respect to W, you're eventually telling this guy how it should improve its or change its parameters to somehow give a better estimate of the data distribution. So we're learning the data distribution implicitly. So the training loop is eventually exactly like what we had before. So there is nothing different. There are only minor differences. So first of all, we are going to initiate some generator and discriminator. Then we start to do sampling. So we're going to make a batch of data samples and also a batch of model samples. So we do know here the model sample generation is very easy. We just sample latent, which are, say, Gaussian noise, and then we're going to pass it through the generator. Then we're going to have a bunch of model samples. Now that we have the model samples, now we're going to compute the output of the discriminator with respect to the model data sample and model sample. This is going to be one sample loss, right? And now we can do it for all the samples inside the batch. And when we are doing it, we're going to, each time we're going to just compute the gradient for the discriminator, right? Now, one point that I mentioned last time as well, so you are going to update this in every iteration. We are going to update the discriminator in every iteration. And then we also define some sort of outer loop iteration, which is Z here. And not in every inner loop iteration, we're going to update the generator. After, say, every 5 iterations on phi, we're going to compute the gradient with respect to W, and then once we update the generator. So we do some updates, say 5 updates on the discriminator, and then we update once the generator. And again, repeat this till we converge, right? And then we discuss this why we are doing it, because we want the inner loop to converges roughly, and then we do one update in the outer loop, right? So that was the idea here. And the only key differences that we have here is that we need to make sure every time that when we update this phi, this discriminator is not going to be something that is not one Lipschitz, right? So we need to somehow enforce this one, this property here, but this is not a big deal. We're going to talk about this. So once we have done, we can just return the train generator, and then we can simply use it to sample from data distribution, right? Now, to just give a kind of summary on the differences between the Wasserstein approach and vanilla approach in GAN, if you look at these two approaches here, so the upper one is the Wasserstein, the lower one is the vanilla GAN. So you can see that we always have a discriminator and generator, right? This is why we call all of them GAN, right? So we have a GAN here again, generator and discriminator. And then out of the output of the discriminator, we are computing some objective which we want to solve the min-max over, right? So the first thing is that the objective here in this vanilla one is proportional to the log of the discriminator output, right? And the reason is because there we are actually defining in terms of cross entropy. We are thinking in terms of classification, right? Whereas in the Wasserstein GAN, the log is not showing up, right? So this means that the output of the vanilla discriminator in the vanilla GAN should be always output of a sigmoid, right? Because it's a kind of probability. In order to have it somehow fitting into the definition of cross entropy, it needs to be between 0 and 1. This is why we use sigmoid, right? But in the Wasserstein, this d is actually the function which we want to be one Lipschitz. So we do not think of it to be necessarily a probability distribution. There is no need to put it to be a sigmoid function. Now, in practice, Typically, we do not activate the last layer of the discriminator. So we do not put any sigmoid or softmax or anything like this. We just get the output of the last linear layer, and then we take it as the output. So it's like a regression problem. Now, the final difference here is that in the vanilla GAN, we can eventually maximize the inner loop over all possible choices of phi. So we're not restricted in the kind of updated neural network we have, but here we should make sure that after update in every iteration, this neural network is still one Lipschitz, right? And this is something that is different as compared to the vanilla GAN. So now, everything, I guess, is clear up to this point. The only key last thing that we need to understand is that how we can make discriminatory, if you're really doing Wasserstein GAN, how we can make it Lipschitz. Now, there are a bunch of computational approaches to do this, numerical approaches. The first one is weight clipping. Weight clipping, it means that you put a kind of limit on the weights inside discriminator. And your discriminator could not have any value out of this limit, right? So it's usually, you would say, okay, I want every weight to be between minus something and plus something, right? And this means that the magnitude of those weights cannot be crazy large. Since they are they're not crazy large, then that kind of Lipschitz, non-Lipschitz behavior is not very likely to happen. And this is why we somehow hope that this approach is going to restrict the variation of the output of the model. But one thing that you should pay attention is that this is not mathematically guaranteed that if you do it for any architecture, this is going to happen. But practically, we see that. I mean, if we do some numerical investigation, we see that this is going to happen. Or if we do some simple or mathematical analysis for simple cases, simple architecture, we can see that for some right choices of the threshold, this is going to happen. So this is the first one. This is the easiest approach that we do. This is the one which was used in the original Wasserstein GAN paper. There are also some better approaches. For example, gradient penalty is a better approach. So the idea here is that you take the gradient of your discriminator with respect to the input. And this is very important to be careful about what I'm saying here. This is not the gradient with respect to the model parameters. If you remember that model parameter, there was phi. Here I'm writing x. This is simply the gradient with respect to input, right? You can always write it down again in terms of your model parameters, right? And one thing that you do know, you don't want this guy to be crazy large, right? So you don't want this to be very large. So what we do, we hope that this guy is somehow going, the magnitude, the amplitude of this gradient is going to be concentrated around 1. If it is concentrated around 1, meaning that for most inputs that we give is all the time something around 1, then this simply means that this is not going to do any harm to the Lipschitz behavior, right? The gradient is limited, so it cannot be non-Lipschitz, right? And to do this, we are going to subtract it from 1 and then take it to power 2 so that we make sure like it's concentrated around 1. And then we add it as a kind of penalty to our objective. And now we try to minimize that guy. So it means that we compute the gradient of the original risk that we have. We compute the gradient of this guy with respect to model parameters. And then we update our model. So this is going to again keep our model Lipschitz, but this is eventually a bit more computationally expensive to do. So you need more computation because you need to compute those gradients here, which is more. Yeah. But this is a very better approach as compared to the first approach. So the first approach is just a simple approach for mm, for proof of concept. And the last idea is what we call a spectral normalization. So one thing, it's not really the last idea. Like there are a bunch of other approaches as well, like among the famous ones. So the other approach is spectral normalization. And the spectral normalization, what it does, so it's eventually normalizing the linear layers, the weights, with the spectral norm of the layer. And the spectral norm is eventually the maximum. I have written here eigenvalue, but this is the eigenvalue of the Gramian matrix. So that is simply the singular value. But I don't want to confuse you here. So if you think of W to be say a square matrix, right? Right now, you assume that W, the weight matrix of one layer. Just think about a fully connected MLP. And then each layer is a matrix, right? Linear layer. And that matrix, say this is squared, then you can take the maximum eigenvalue. And then that is basically proportional to your spectral norm. But in reality, this is not a square matrix, right? Then you don't have the matrix itself, but you're going to put matrix times matrix Hermite, right? So the matrix time matrix transpose. And that one is going to be squared. Then you can compute the maximum eigenvalue of that guy, which is eventually the maximum singular value of your matrix. And then you divide this matrix with that guy. So eventually, the point that is happening here, spectral norm is computing the value of the direction where the matrix is actually having eigenvector or eigen changes most extremely. And then it's going to make that direction, the value in that direction to be 1 when you normalize it. And anything else is going to be smaller than 1. So it's somehow implicitly doing what we have here, right? But in a more, say, advanced way. So you can still make sure that the weights are here somehow bounded, and out of this boundedness, you get a sort of Lipschitz continuity in your function. So this guy, the third one, could be as good as the second one. Sometimes it could be less good. Something could be more efficient, but it's again computationally expensive. And typically in practice, if you want to just do, one initial experiment, not very sophisticated, you're going to do weight clipping. If you want to do very sophisticated one, you're going to stick to gradient penalty.